question is why?
From Zoom.
Okay. Yeah. Okay. Yeah. Why 1925? Well, thank you. 1925 was the people have been getting hints of quantum, the role of quantum mechanics in physics, which I'll describe in great detail. But it's only in 1925 that the first real predictive theories began to be formulated. This was by Werner Heisenberg, who formulated what was soon called matrix mechanics, which all students learn. I'll say more about it in a little while. And for those of you who are physicists, here is the basic formula that transition amplitude is given by such and such. Now, I want to emphasize in this talk, this is going to be a completely non-technical talk. However, just to make sure the physicists in the audience stay awake, I have a little bit of physics formulas every now and then here. So, okay. Yeah. Now, what is this quantum mechanics? For those of you who don't know, it is the basic theory that physicists use to describe the microscopic world. There are several fundamental ideas that come into it. One is that when you measure something, the measuring process always has an effect on what is being measured here. In the classical world, you can measure the length of a table, and the table will stay put, not know it's being measured. Anything you try to measure in the microscopic world, however, knows it's being measured, and its state will be changed. This funny business that particles are sometimes described by waves, and waves are sometimes described by particles, which was an idea that was not well understood in the beginning. And the thing about these waves is they can interfere, and interfere with each other, just like water waves can interfere. The other strange thing about quantum mechanics compared with classical mechanics is that results are probabilistic. You can give the probability of some event happening, but you cannot predict with certainty what the result of a measurement will be. And quantum mechanics to this day remains a strange subject. It works. It works beautifully. It works better than any theory to date. However, there are problems that people do not understand, and the main one that's not understood is the role the observer plays in the measurement. Should the observer sees a quantum mechanical system doing something, but should the observer be counted as part of the quantum mechanical system? I'm not going to discuss this, but it's an open. It remains an open, not well understood issue. Okay. Now, what I want to discuss, even though this is the 1 century of quantum mechanics officially, 1925 to 2025, I want to discuss a different century. I want to discuss the century that began in the late 1880s, when people were just trying to understand colors. For example, how in a blacksmith shop, you work hot metal. The metal will glow reddish or yellow, greenish, yellow or red, depending on temperature. We're certainly familiar with ordinary electric stoves have glowing red at 800 degrees centigrade. So the question I wanted to ask is, how do we go from people thinking about where these colors came from? How do you describe the colors? All the way to smartphones. These things in just 1 century. It was quite an amazing century here. That's what I want to talk about. This bottom picture shows you the temperature, the colors that metals will show as the temperature rises. Celsius is on top here. Okay. Now, how to understand the colors? So this is one of the first things that happened. This in the 1890s. This was a major problem in physics. How, as you change the temperature, did the brightness of metals change, and what was their color? And this shows a spectrum of black body radiation versus wavelength, increasing wavelength here, and the bluer the light, the shorter the wavelengths involved, the redder the light, the longer the wavelengths, and less bright it is. Where did this come from? People really had no way of predicting it. They could predict sort of what happened at very long, very high wavelengths, very long wavelengths, but they had no understanding of the peaks and such. Then in 1900, the German physicist Max Planck, he was just playing with this, and he did a simple trick. He said, suppose that the light the light that he's trying to describe comes in little bundles, which not light doesn't come continuously, but little bundles. These bundles we know eventually are identified as photons. But he said the light would be emitted only in little bundles with energy proportional to the color or the frequency of the light. And he said the energy was just some number times the frequency of the light emitted. This little number, he wrote down H. This eventually became known as Planck's constant. And we're all familiar with Planck's constant with a little bar through it, means you divide by 2 pi. And so the result that Planck derived was that if you have a black body, radiation, the number of photons goes to e to the h bar, speed of light times the wavelength, the wave number of the light divided by Boltzmann's constant temperature at -1. And he derived this formula, but had really no idea of what this, the fact that the light came in little bundles, where that was coming from here. Now, one thing you should note about this is notice rule of temperature here. The first attempts to understand quantum, the first place when we began to see quantum phenomena was in statistical physics. As we'll see, the atomic root was the whole other track into the problem. Okay, so a second weird effect was called the photo effect. Heinrich Hertz, and he's we're all familiar with megahertz. This is Hertz at megahertz, and nanohertz. So it's nice to have something like that named after you. Mega Baym, micro Baym. What he did, he in 1887, he shined light on a metal plate, his original apparatus, and he shined light on the plate, and electrons were emitted. So what he actually had was a sort of this chamber here with the metal on one side. When he shined light on the metal on one side, that's shown over here schematically, electrons were emitted and absorbed on the other side, and he saw a current in the circuit here. And the question is, why, when you shine light on a metal, should electrons be emitted? Was a complete mystery. Nobody had any understanding in the late 1880s, how such an effect could occur. Okay. Well, Albert Einstein in 1905 came out with a solution to the problem, for which he got the Nobel Prize. Nobel Prize was just beginning at this time. In 1905 for Einstein was an incredible year. It's called the Anno Mirabilis, which means the year of miracles in Latin. And he published 3 papers that year, one on the photo effect. He did special relativity and also theory of Brownian motion. Spectacular physics, each of them. 10 years later, he did the theory of general relativity. Well, what Einstein said was that light actually came in little bundles called photons. And you could understand the photo effect by the energy of the light. The light is absorbed by an electron. If it has enough energy, an electron will pop out. And so for this, as I said, he got the Nobel Prize. But in fact, if you think carefully about it, in fact, if you've ever taught quantum mechanics, you realize the photo effect does not prove the existence of photons in the least here. And when you teach quantum mechanics, you always just describe the photo effect in terms of a classical electromagnetic field falling on the surface, falling on the metals. And what the photo effect really shows you is that electrons obey quantum mechanics. It does not prove that light obeys quantum mechanics. In fact, to see the light, I'll come back to the subject. Why? Do we really know there are photons? Oh, okay. I just to emphasize the point, you don't have to follow the details here, but I emphasize, you know, when you teach quantum mechanics, you don't invoke the quantization of the electromagnetic field. You don't invoke photons. And so I just looked at some old notes of mine when I taught quantum mechanics. Is there? Oh, sure. Bye. Okay, okay. Where's the camera? Yeah. Okay. Yeah, okay. Great. Um, and what you do, just for the physicist, is the way you go about describing the photo effect. You take an interaction, a classical external field, A, is just a bunch of numbers coupled to electromagnetic current. Now you let the current be quantum mechanical, but this is just classical. And you do a Fourier decomposition of it, and you calculate the rate of absorption, and you get the right answer. And you get the appropriate thing over here that says the change in the energy of the electron is just proportional to the frequency of the light times Planck's constant over here. But the key here is that you put in the quantum mechanics of the electrons. And so this simply does not prove the existence. The photo effect does not prove the existence of the photon. But Einstein deserved the Nobel Prize anyhow. That's okay. Okay. Now, there was a whole other track going on in quantum mechanics. And this began with Ernest Rutherford. Ernest Rutherford grew up in New Zealand, but in 1911 or so, he moved to Cambridge. He came to Manchester in England. And he's really the guy who's responsible for what we understand the basic structure of the atom. He got a Nobel Prize in chemistry in 1908, where he looked at the radioactivity of the various elements, which is not part of the present story. Then he did a wonderful experiment in 1911, where he shined alpha particles, the helium nucleus, on gold, and he saw the alpha particles scatter at large angles. And this told him that the inside the atom, there must be a little hard center. This hard center was the nucleus. And so this is the way he discovered the nucleus. And so thanks to Rutherford, the picture of the atom is that there's a little nucleus in the middle with the electrons running around outside of it. And then in 1918, he discovered the proton. And when he did this, he shined alpha particles on nitrogen gas, producing a proton plus other things here. And he identified the proton as sort of the building block of the nucleus here. He was rather opinionated person, Rutherford, and he has his quote, all science is either physics or stamp collecting. Does anybody collect stamps anymore? No, but they did back then. Okay, so here's the atom. And there was the old J.J. Thomson model of the atom, which is called the plum pudding model. It must have a nice name in Japanese also. And here he described Thomson's picture was there's a ball of positive charge with individual electrons running around in it. And if you did the scattering that Rutherford did, you shine alpha particles through, they basically just go through, not very disturbed. However, Rutherford's picture was just a tiny little thing, the nucleus in the center, which is 10 to the minus 13 centimeters. It was a 10 millionth of the size of the atom itself. And so the alpha particles go through the atom, but sometimes they hit the center. And because the center is very hard, they get deflected at large angles here. And that was the evidence for the nucleus here. And as I said, then he discovered the protons. So the picture we have of the nucleus, of course, is that when it's protons, the little blue balls, positively charged, and the little red balls are neutrons. But these were discovered only later, 1932. Now, this is a wonderful picture. This is J.J. Thomson, who discovered the electron. Rutherford was Thomson's student. here. Thomson discovered the electron. Rutherford discovered the proton, and he had a student called James Chadwick. And what Chadwick did was discover the neutron. And so this was just 3 generations, quite amazing. And if you think about it, between the electron, the proton, and the neutron, this is the making of a deuterium atom, a piece of heavy hydrogen. These 3 guys in academic order discovered it all. It's quite nice. Okay. Now, there was a question. I assume you're all familiar with the idea of atomic spectra. If you heat atoms, they will emit light. But the colors of light they emit are very special. It's not a continuous spread of colors. And the sun, because of a lot of atoms and a lot of scattering, has a basically continuum of light, but there are distinct spectral lines here. And in fact, that's, for example, how the element helium was discovered, because one saw special lines in here that are associated with helium, these lines over here. Hydrogen has also a set of lines, mercury, and so on, uranium. All atoms, when they heated, emit certain lines. The question is, where did this come from? Why did atoms want to do this? Well, we turn now to Niels Bohr. Bohr is, I think, rightfully the father of quantum mechanics, the person who put everything together, all the pieces together. And in 1913, he came out with a model of the atom that began to explain the spectral lines quite well. It didn't explain why it worked, but his model of the atom worked, but it appeared to explain the lines. And in the 20s was really devoted to understanding, bringing quantum mechanics into the version that we know today. Here, this is the famous Bohr Institute in Copenhagen, which started in 1921. And this is a picture of there's this famous auditorium called Auditorium A in the Institute, where you see all the great men of physics here: Bohr, Heisenberg, Pauli, and so on, Landau. And anybody know what that is? Constructive Photoshop. Yeah. What was interesting about Bohr didn't immediately accept the existence of the photon. He wasn't worried about this all his life, and I'll come back to that story at the end. Even though Einstein sort of postulated the photon, Bohr didn't accept it. But Einstein, on the other hand, didn't accept quantum mechanics. There was constant tension between the two of them, always a very productive tension. Yeah. The Bohr atom was developed in Manchester, and Bohr wrote a grant application. And those of you who apply for money nowadays will really wish for the old days where this was his grant application in full. And it's Copenhagen here. Copenhagen, June 20th, 1911. The undersigned permits himself to request a travel stipend of 2,500 kroner. And this is Goman N in today's exchange rates for a 1-year study stay at foreign university. Sincerely, Niels Bohr. And he wrote this to the Carlsberg Foundation. They gave him the money. And isn't that amazing? Try that now. I said, well, here's the Bohr atom. By the way, I just show this here. The Bohrs and the Rutherfords were friends. This is Niels Bohr, his wife, Rutherford and his wife, and they were close personal friends. What Bohr postulated was that electrons in the atom, when it's a nucleus, the electrons went around in special orbits. Now you know that the Earth goes around the sun, but the Earth it's an accident where the Earth is compared to the sun. The Earth's orbit could be a little smaller, a little bit larger. Anything according to classical mechanics is a possible orbit. But he said they only had very special they rely only on electrons could only go around in certain special orbits. I'm not going to show the details of them, but then he postulated that when an electron jumps from one orbit to a lower orbit here, it would emit light. And so this is hydrogen, where you go from the n equals 3 to the n equals 2. line. The light is 656 nanometers, and that the frequency was just the difference in the initial and final energies of the orbits divided by Planck's constant. And here you see for the first time in atomic physics, so in mechanics, not statistics, but in mechanics itself, you see the presence of H bar, or H Planck's constant coming in. So this is a whole separate train here. Now, interestingly, Einstein in 1916, the Bohr atom was 1913. Einstein in 1916 developed what it called his A and B coefficients. Are these things still taught? Yeah, this is very, very important because Einstein at this point made the connection between the statistical mechanics with photons and the probabilities of light being emitted by atoms. And it was really this result that tied the two approaches, the two parts of quantum mechanics, the statistical mechanics, tied together with the mechanics. And his argument, just briefly, is that if you have a cavity, sort of box, and then light's being absorbed and emitted. But if it's just at a certain temperature, the number of photons will remain exactly the same. So the rate at which photons are absorbed is the rate at which they're emitted. And he went through a simple argument, which I'm not going to go into the details of, which said that how do you get Planck's result from this? He said, well, imagine simply you have two-level atoms, a lower state and an upper state. You can get absorption. A photon can come along, take an electron in the lower state, boost it up to the upper state, or an electron in the upper state can just jump down to the lower state, emitting a photon. And by considering the rates of balance of these two, and plus the crucial fact also from statistical mechanics, which is that at temperature T, the probability of the upper state being occupied compared to, these are electrons, the probability of an electron being in the upper state compared to being in the lower state is just given by E to the minus the energy difference divided by Boltzmann's constant times temperature. So he used this result together with these simple statements about the rates, that the rate at which atoms would be absorbed is just some constant, is B. You never had to write down the constant. B times the number of photons that are present times the probability they'd be at the lower level is occupied. And he went through the same argument for the emission from the upper level. This would be the probability this is the probability you have an atom here, an electron here to absorb the light. This is the probability of the electron in the upper state to emit the light. Now, certainly, if there was no what's called spontaneous emission, the probability of P0 is the probability of being in the lower state is bigger than the upper state, and therefore all the photons will eventually be absorbed. And this system will become dark. And so we said, well, we need to have called spontaneous emission, where the rate is pushed to some number called A times the probability of having something in the upper state. And to maintain a steady state, this has to be zero, and you do a quick calculation, and you find A has to be equal to B. And what's beautiful about this argument is that it connects the absorption and emission probabilities, which are things that one could eventually calculate by atomic rules, microscopic rules. It connected that with the statistical mechanics, which was telling you what the distribution, the number of photons would be in the cavity. Yeah. So this was really quite a crucial point in the intellectual development of quantum mechanics. It was the wrong way. Yeah. Okay. Then we skip ahead a little bit to 1924. And Louis de Broglie, here he is over here, looking very thoughtful. He proposed simply that matter, microscopically, matter would behave as waves. I mean, there was this strange mystery of one knew that light were waves, in the form of waves, and yet they could somehow behave as particles in the photo effect, for example. And he said, well, maybe all matter could behave as waves, electrons too. But he did not really understand what was going on at the time, but he said it. And then what he proposed, however, is that um, the these waves, with electrons or atoms or whatever, can interfere, and you get nice interference patterns like this. And that turned out to be pretty good, pretty true. I mean, the first experiment that really showed the interference patterns was by Davis and Germer in 1927 using electrons. And this is a standard picture of the two-slit diffraction. You have a beam of light coming on. It goes to a little aperture, expands out, and then goes to two slits. This is called Young's double slit experiment. And the wave that goes through A interferes the way through B, and you get this characteristic pattern on the screen where it's brightened in certain lines alone over here. What you see experimentally is that if B is shut, if there's no opening over here, you will just see a characteristic line, a blob here that's along the screen here. You see a characteristic blob of the light going through A alone. On the other hand, if both slits are open, A and B, then you see this detailed interference pattern here. Bohr was very interested in this, and what was amusing about Bohr is he loved to build models, and this is he built this model, or probably didn't do it himself. He had people in the workshop at his institute build them. This is a picture of his model of the two-slit diffraction experiment over here. He always thought in terms. We're always thought in terms of such real mechanical models here. He learned that in school. He learned it when he was a young child, he was 6 to 10 or so. In school, he spent a lot of time building models. Okay. And so the question was, what was he was these waves? What was the meaning of these waves? They could interfere with themselves, but what was not understood at all. Schrödinger, who in 1925 invented something called the wave equation that could describe de Broglie's waves. But the problem is we're all familiar with the Schrödinger equation now. It's sort of the basic thing you've learned in elementary quantum mechanics. You just use it to describe all hydrogen atoms and other systems. And these are sort of pictures of the waves in hydrogen, and the lowest energy stages, the blob, states with higher angular momentum, the waves begin to have this angular structure and so on. But Schrödinger didn't have any idea what these waves were either. He thought the waves were the particles themselves, which somehow photons were particles, the photons would be waves. Well, maybe particles, these waves were the particles. We know that's wrong now, completely. Okay. And then in 1925, this is the year we're celebrating now, the 100th anniversary, Heisenberg began to try to make sense of this. I mean, Bohr did not have a mechanical picture. He didn't say why, what connection there was between his how the emission occurred. He said that it would, when an electron jumped from one orbit to a lower one, it would emit light, but he didn't understand. He didn't try to explain what was happening there. So Heisenberg knew that somehow, if light of frequency, some frequency omega is coming out, something must be moving at that frequency omega. And this is a standard way, radio stations have occurred at frequency omega, and they emit radio waves at frequency omega. So he asked himself, what was going on? He said, well, there was an electron. You have an electron moving around, and he thought in terms of what physicists call Fourier components. So what were the frequencies? He said, well, if something must be going on. The electron must have some motion. If it makes a jump from level N to level M, it must have some motion that involves things wiggling with such a time dependence here. And I'm not going to go into details of matrix mechanics, but he began to write down such objects here describing the motion of electrons. And he invented from this what we call the Heisenberg equations of motion, which you're all familiar with. Except Heisenberg did. If you actually read Heisenberg's paper, you don't see it written out clearly there. What you do the uh, our present understanding of it is really due to Born and Max Born and student Pascal Jourdain, Jordan, realized that well, these things were simply matrices. And Heisenberg had things, matrix was multiplying these things together. But he didn't realize the rules were simply ordinary matrix multiplication because he never learned about matrices. But Jordan was very good. And so they simply reformulated the theory in terms of matrices. And this was just immediately after late 25. And at this point, the quantum mechanical matrix of mechanics was established as a predictive theory here. Then came the interesting question. Born really was quite spectacular. He began thinking about Schrodinger's wave amplitude, what the meaning of it was. And what he realized is that the square of the wave, in fact, tells you the probability that you find a particle over here. And so he wrote down the famous things that the probability is just the absolute value squared of the Schrodinger wave. This was really quite a spectacular advance because it's the first point at which quantum mechanics loses its deterministic character, becomes a probabilistic theory here. And Einstein kept objecting because he said God does not roll dice. And in fact, according to what we learned here, is God does roll dice. Okay. Then Heisenberg went a step further. And in 1927, he realized the uncertainty principle, which says simply that one cannot determine the position and speed of a microscopic particle at the same time. This is the thing we observe, the uncertainty in the position times the uncertainty in the momentum or velocity is bigger than half of Planck's constant over here. So by this point, things were beginning to come together. One had the matrix of mechanics and the wave mechanics, which were eventually proved to be equivalent by Dirac at just about this time, were become an accurate predictive theory of nature. Now, one point about the measuring the microscopic world, I mentioned is that when you do a measurement, the measurement in the everyday world, the classical world of big things, when you make a measurement with a light beam, for example, you shot a laser at some distance, and you figure out what the distance is. It doesn't affect what's being measured. If you microscope, but suppose on the other hand, we didn't have such fine tools as lasers and such. Suppose we had to use, I say bowling ball. Do people know what bowling is? There's this game where you take a big ball and roll it, knock pins over. Suppose you had to use bowling balls for measure. No. I'll come back in. Yeah. Suppose you had to use bowling balls for measuring, and you sort of want to measure where the pin. You want to measure where are the pins. Well, you throw a bowling ball at it, and it's pretty hard to throw the ball so it exactly hits the pin, and you can see it. What it does, of course, will always knock the balls over. And so this is the classical analog of how when you do an experiment using, for example, electrons hitting things or light, you will disturb the system. Okay. And if you think about how to measure things in the atomic world, if you want to measure position of an electron, you use light. Light has a long wavelength. If you want to measure accurately, like using a finer paintbrush, you have to use more energetic light, which has a shorter wavelength. Shorter wavelength has more energy. The higher energy will kick the electron and sort of disturb where it is. And this is the physical origin of Heisenberg's uncertainty principle here. Okay. This is a very, very funny example. This is nothing to do with quantum mechanics, but just it's sort of a nice analog of trying to measure the world. Can you see the black dots? Did anybody not see black dots? Huh? You see black dots at the intersections, but if you try to count them, you can't. It's not really quantum mechanics, but it's amusing. This is called, in psychology, it's called the Hermann grid. Yeah. Okay. Well, by the way, this is just a very, very nice picture of Heisenberg Bohr, Heisenberg standing here. He is about 30 years old here, and his Bohr was 16 or so years older. What's wonderful about this picture is that they're on a vacation here, but Bohr's sitting taking notes. He does all the time. Yeah. He played football, so soccer, and in high school, and he was standing there, the ball's coming, and he's standing at the goalpost doing a calculation on that. It's good. Okay. I want to turn to this question of the reality of the photon, but also the reality of the connection of waves and particles. And the beautiful experiment done by Akira Tonomura and Hitachi. The experiment was done in 1988, where he was. This is showing you he's building up, sending through electrons through a double slit, and building up the diffraction pattern one at a time. So here's a picture with 10 electrons, 100, 3,000 electrons, and 20,000. And you see, by the time he gets to 20,000, how well the pattern's built up. And so if this works, nope, it doesn't work. No, no. Uh, uh, oh, only trouble, there's no cursor here. Oh, patience. Huh? Can you get the cursor right below there? I can't. That was good. Upright. Is running good? Okay, fine. Thank you. So you see 3 dots, 4 dots, and so on. And eventually it builds up, and you get this beautiful diffraction pattern after 20,000 electrons. I mean, this is one of the great experiments in physics. Okay. There's a question. I mentioned whether photons are real or not. The Einstein photo effect, Einstein's explanation did not prove the existence of the photon. In fact, all physicists didn't like the idea of the photon. I mean, Planck, who's really the first person who wrote something down, that you showed that the black body required electrons coming in little bundles. He said, rejection of Maxwell's electromagnetic waves seems to be a step which is not yet necessary. This is 1909. His Planck's formula was 1900, 9 years later. Planck with Nernst and Rubens, I don't know. 2 years later, they write the fact that Einstein has now and then overshot his speculations. He's gone too far. As for example, with his light quantum hypothesis, should not be held too strongly against him. Without a certain amount of risk, there cannot be any real innovation, even in the most exact of sciences. So it was okay to Einstein to say this, but we shouldn't hold it against him for inventing, for speculating on photons, because it couldn't be real. Millikan, who did the famous oil drop experiment, he said Einstein's bold, not to say reckless, light quantum hypothesis flies in the face of the thoroughly established facts of interference. He didn't know yet about Tonomura's experiment. And even Bohr, in 1925, he said, well, even if Einstein sends me a cable, a telegram, that has an irrevocable proof of the physical existence of light quantum, that an irrevocable proof has been found, the message cannot reach me because it has to be transmitted by electromagnetic waves. He felt that if you had photons, you couldn't have waves anymore. Let me say, people were quite confused at this stage over here. Bohr kept wondering why there were photons. And interestingly, I came as a postdoc to Copenhagen, to the Bohr Institute in 1960. And this fellow, Owen Peterson, he was sort of Bohr's scientific secretary. He had a PhD in physics. He was a physicist, but he was quite close to Bohr and his wife and Owen Peterson here. And he told me a very strange experiment that Bohr thought of, that ordinary quantum mechanics would be the consistency of ordinary quantum mechanics at the level of two-slit diffraction requires that photons exist. That's all I knew. I knew a little piece of the argument, but nothing was ever written down. And so in Tomoki Ozawa, who is now in Sendai, he was a graduate student in Urbana. This is the two of us immediately after the 2011 earthquake in Tokyo, wearing our helmets. We actually worked it out. I just want to give you the basic idea here, which was that suppose you do ordinary two-slit diffraction experiment over here. Now, one electron at a time, just like Tonomura did. And the trick is you try to measure the electric field produced of the electron far away. So this is a little ball that will move depending by whether the field is strong or weak. It will move more or less. And too far away to the measurement to affect what's going on over here. The electron hits the screen and makes a spot before the light has time to travel up and back. And so really what you could do is if the electron goes through the upper slit, the Coulomb force will be stronger than if it goes to the lower slit. Therefore, you could, in principle, measure which slit the electron went through. Now, we all know from quantum mechanics that if you can measure which slit the electron went through, then the diffraction pattern, the interference pattern, must be destroyed. Somehow, the pattern is not destroyed. Davidson and Germer really did this back in 1926. They found the interference pattern. So what's going on? It's really when you try to measure the electron far away, the electric fields in the vacuum that really make the measurement quite difficult. And in fact, you cannot, with ordinary electrons, ever do the measurement. But if you read the quantum mechanics books, you never see any mention there that two-slit diffraction depends on the charge of the electron. But Bohr was saying it must depend on the charge of the electron. So imagine you make the electron have a very big charge, so 100,000 or a million ordinary units of charge. At that point, you can overcome the uncertainty in the detection, and you can actually measure which slit the electron goes through. Okay. Now, you don't need to do the measurement. All it's telling you is that when the electron has enough charge, what it does, it starts here, it goes by the upper path or the lower path. When an electron turns a corner, it radiates light. That's a classical radiation. What you learn from this thought experiment is that as the electron turns the corner, it will emit light. And if the charge is large enough, it will emit enough light to change the phase between the two paths. It doesn't simply shift the phase. And in the famous Aharonov-Bohm experiment, where a magnetic field makes a phase difference. But what it does is it destroys the phase information here. Right? It destroys the pattern because the phase of the upper electron becomes uncertainty compared to the phase of the lower electron. And so it was this conceptual argument that Bohr had that showed that the electron must carry away phase information. And if it can carry phase information, then it must be an independent degree of freedom, must be quantized, and therefore photons exist. That was it was quite beautiful argument here. So Bohr, unfortunately, had died by the time we wrote up his ideas, but I mean, he would have been very happy. Okay. Now, there's a few other things going on in quantum mechanics, which one is the idea of superposition, that one can have, if you have a wave describing a particle moving to the right and another wave describing a particle to the left, you can add the two together. If you make a measurement, there'll be some probability of the electron moving to the right, some probability of moving to the left. And this is a very interesting idea, but this raised also the question raised by Schrödinger. Schrödinger tried to say, how far can one push this idea? And so he has the idea of Schrödinger's cat. Schrödinger's cat is sealed in a box. There's a radioactive material over here. If the radioactive material decays, it comes out, it will trigger, comes out by the upper path instead of the lower path. It will trigger a hammer, which will hit a glass jar. Glass jar is full of cat poison. This breaks and the cat dies. But there's only some probability of amplitude, some superposition of states of the radioactive particle going out the upper or the lower channel here. And so the result is that the cat is in a superposition of dead and alive states. This, of course, is completely unreasonable to us. And indeed, there is a fundamental question of to what extent does quantum mechanics describe macroscopic objects in the world? I won't go into that, but it's an important subject here. And so this, by the way, has given rise to a number of good cartoons. In the hospital, about your cat, Mr. Schrodinger, I have good news and bad news here. Or this is also good. This is the analogy with dishes over here. The dishes are both broken and unbroken until you open the door, and you do the measurement. Okay, I want to turn a little bit to the last few minutes to this question of the technological development, and so by 19, just one other important feature that we see plays a big role is quantum tunneling. If you send an electron against a big field, if it doesn't have enough energy to pop over the top, it'll just bounce back. You know, if you throw a ball against this ball here, it'll just bounce back. On the other hand, in quantum mechanics, if you send an electron at a barrier, it has a certain probability that it can actually go through the barrier. So what is called the process of tunneling. This was certainly studied by Friedrich Hund in 1926, right after matrix mechanics. And it, in fact, turned out to be a key concept in solid-state electronics here. What you can do is, in electronics, you control the current going through a barrier. You can control the current by changing the height of the barrier. And that's really the key of smartphones. I'll come back to this in a moment. Okay. Another key ingredient that was discovered just around this time was the electron spin. Ralph Kronig, a German who spent a lot of time in America, he was trying to understand the magnetic properties of atoms. And in early 1925, just 100 years ago, he proposed that electrons were spinning in one of two ways, clockwise or counterclockwise. This is the famous electron spin. He had it completely right. Pauli and Bohr said, no way, impossible way. They wouldn't accept it. But then Uhlenbeck and Goudsmit in the Netherlands independently proposed the idea of the electron spin, and somehow that stuck. Now, with Pauli in 1924, this is before the matrix of mechanics, he still had the Bohr atom. He proposed the exclusion principle, which says that only one electron spinning in a given direction could be in a given state. So when Bohr draws these orbits, each orbit could have possibly two electrons, one that spins one way and one that spins the other way. And we know the exclusion principle really began to give us a first understanding of why there were chemical elements, the different arrangements of possible arrangements of electrons inside atoms. Here, that was all very good. And so, really, by 1926, I would say the fundamentals of quantum theory were all in place, and that at this stage, the problem turned to how do we begin to understand things of the real world? How do we understand real atoms, complex atoms, real molecules, real materials, many particles all together? So there's a matrix of mechanics, the uncertainty principle, the ways of describing particles. Quantum mechanical atom had spin, like comes in little bundles, the photon. And so the question is, how do we go about trying to understand many particle systems? Now, I have to point out that you probably all know it, that particles come in two types. There's what are particles that obey the exclusion principle. They are called fermions, named after Fermi and Dirac, paper 1926, that says some particles will behave this way. And we know now electrons, protons, neutrons, helium-3 atoms, they all obey what are called Fermi-Dirac statistics, they're fermions. Now, there are particles that don't obey the exclusion principle. For example, photons. If I would have two laser pointers and I shine them on fermions, you cannot get two in the same place. In the same way, you cannot park two cars in one parking space. That's forbidden. On the other hand, if you turn on the lights over here, everything gets brighter. Two lights can be in the same place. The photons can be in the same place at the same time. So ordinary light or photons are bosons. They simply do not obey the exclusion principle. And then there are things like helium-4 atoms that also are another example of bosons here. And one refers to this as different kinds of particles obey different statistics. So at this stage, Pauli decided he would want to ask the question in 1926, what statistics, what do electrons and metals obey? Now, this is a funny question, because Pauli, in late 24, wrote down the exclusion principle, saying you can only have one electron in any state with certain spin in an atom at the same time. So he set out to find out what the answer was for electrons, just to do a test. And what he did, he analyzed paramagnetism of metals. He had very bad data and very most rudimentary theory, and they agreed perfectly. If he had better data or better theory, he would be confused. But at the time, it was a lucky accident. And he concluded that electrons obey Fermi-Dirac statistics. They're fermions. We said, so what? We all know this. However, he wrote a letter to Schrödinger saying, with a heavy heart, means I'm really sad. I feel bad about this. With a heavy heart, I become converted to the idea that Fermi, not bosons, Einstein-Bose, is the correct statistics. Somehow, he was thinking that the answer had to be that electrons in metals had to be bosons. I don't know why. Now, but you would think this is completely crazy, because here's the guy who invented the exclusion principle. He knows all about electrons. And that's really, we can say that looking back. But we don't, at that time, one did not understand it. There are two possibilities, that the properties of electrons depend where they find themselves. Electrons in atoms obey the exclusion principle. Electrons in metals do not. That's certainly a possibility. As we learn eventually, thanks to experiments and Pauli's theories, we know that electrons, whether the particles obey the exclusion principle or not, is a property of the particle itself. Yeah, but that took a long time in the 30s to be established. And in fact, in the first experiments on liquid helium-3, which were done in 1957, the first experiment really set out to prove the original Pauli paramagnetism experiment to show the helium-3 atoms in liquid were, in fact, Fermi particles here. And it's an idea that slowly snuck in. Well, anyhow, but this discovery that the electrons are fermions really is the beginning of the quantum theory of solids here. The first realistic quantum mechanical calculations were done by Seitz and Wigner in 1932, where they calculated what the binding energy of sodium metal would be. This is what we know now as the Wigner-Seitz approximation. Okay. Now, the question, why are some solids electron conductors and some are insulators? Well, we know that in atoms, only special orbits are available in the Bohr sense. And in a solid, that in a lattice, where you have electrons and nuclei, not all states are available. You have sort of a continuum of states. These are showing different momenta here. Now, the continuum of states, but there are gaps in between over here. These so-called energy gaps, which play an important role in solids. This is actually a picture from Rudolf Pauls in 1930 showing the gaps. He invented the band theory of solids. And the idea is simply that if you have a gap, if you fill up all the states in the lower band, have a gap and an empty state up here, no current will flow. That's an insulator. On the other hand, because if the electrons fill up further, then electrons can flow in the upper state over here, and that's a metal. So when one really began to understand the difference between conductors and insulators, also semiconductors, just in terms of this picture of what the possible states are inside electrons in a lattice. That was an important advance. Now, I just want to spend a few minutes just talking about how we got to smartphones here. It turns out quantum mechanics is very important. I don't have an accurate figure for this, but a few years ago, it was estimated that the gross domestic product in the United States, about 1/3 of it depends on quantum mechanics. And if you think what goes on, electronics, television sets, computers, all that stuff, control systems, in the medical industry, magnetic resonance imaging, lasers like this one over here, oops, lasers, automobiles. Turns out standard automobile now contains between 1,000, 10,000 chips, integrated chips, without which cars don't work. You know, as little I could fix any car, but now it's completely impossible. You can't do it. You have to buy a new chip and put it in, and etc. And then the question: how did this development happen? It's a very interesting story. The telephone was invented by Alexander Graham Bell in 1876, and he spoke to his assistant, was called Watson, and said, Watson, can you hear me? Come here. And, that was the beginning. Then people thought this is a great invention, that they would go on and make. They would try to speak further, and so in 1892 there was a telephone call between New York City and Chicago, shown on the map over here, from here to here. That was pretty good. And then by 1915, they're able to have the first transcontinental telephone call from one side to the other. 1915 was an interesting year. This is the year before Einstein A and B coefficients. And it turns out 1915 was not only the first transcontinental telephone call, it was the first highway across the United States. You could actually drive from one end to the other on real roads. And furthermore, it was the first airplane flight that went across the United States. All three of these things happened simultaneously here. So this is Bell himself drawing, talking on the telephone in this 1892 call to Chicago. Now, and so there was this promising idea of being able to have telephones all over, except the signals were very weak and you had to amplify them. And so, and there's the first, I mentioned, first phone call in 1915. You had to amplify the signal, but how do you do it with vacuum tubes? Everybody remember a vacuum? Anybody old enough to remember what a vacuum tube looks like? How many people have actually seen a vacuum tube? Yeah. But they were not practical at all. I mean, the vacuum tubes were, somebody wrote, large, expensive, fragile, slow, noisy, and reliable and short-lived. And there's just no way you could make enough vacuum tubes to set up a reliable telephone network. And so Bell Telephone Labs, in the early 30s, at the very beginning of the quantum theory of solids, they realized that solid-state electronics, using new quantum mechanics to build solid-state electronics, is probably the right answer to the problem, as we know it was. And so they began in 1936, really directed research at trying to invent a solid-state amplifier. And the first silicon junction was 1940, and then World War II came along. That interrupted work. Actually, World War II contributed one important thing, which is the idea of zone refining. Zone refining was a way to make very pure metals, and so thanks to that, one was able to make things like pure germanium, very pure silicon, which enabled the invention of the transistor. And so, 1947. Now, this is. Bardeen, Bratton, Shaw invented the transistor. This is very shortly after the end of the Second World War. The Second World War ended in 1945. And what they had designed here was a point contact transistor where the, there was a piece of material over here. This is the original material down here, and where an electron would somehow tunnel from here into the lower layer over here. Now, several things, comments here. Well, this is a classical picture of Bardeen, Broughton, and Shockley. Shockley at this point had nothing to do with it. He had worked on it in the 30s, but he really at this stage was just looking over people's shoulders and saying, good job. However, when time for the photographs, he was, of course, the center of here. Bardeen actually left Bell Telephone Laboratories, came to Illinois very shortly after this. And one of the things in the mid-70s, in 1977, there was the 30th anniversary of transistor, so we baked him a cake. This is a photograph of the original cake. This little triangle over here was in the shape over here, and all these black wires were edible licorice here. That was great fun. And Bardeen enjoyed it tremendously, the cake. Well, and so what was interesting about this experiment, though, is that what they wanted to make was a field effect transistor. So this was the idea that electrons would tunnel through a barrier. This particle going over the barrier classically, and through the barrier quantum mechanically. But what they did, just to make sure everything just worked right, they washed the apparatus. And there was a very thin layer of there's gold here, and the upper plate was gold, and it had a little layer of gold oxide on it, which they unfortunately washed off. And so what they invented was something where the electrons actually sort of jumped straight through without tunneling. This is called the point contact transistor, and that was not what they wanted. I mean, it was a sad mistake. And Bardeen said it set back transistor research by some 5 years or so. Shortly after this, they realized that this was not what they wanted, and they developed the field effect transistor. But nonetheless, Bardeen, Broughton, and Shockley got the Nobel Prize for this, even though Nobel Prize for a mistake here. It was a good mistake. After this thing, the ideas were basically in place, and the idea was how do you begin putting multiple transistors into the same unit, and then there was the chip and the integrated circuit, putting multiple transistors all together, and according to Gordon Moore, as he showed in his funny graph here, the number doubled every 2 years, Moore's law, which is we're probably running out at this stage here. And so, interestingly, the present smartphones, this guy over here, I figure out how to get back. This thing over here has something like 20, a little chip, which is roughly a centimeter by a centimeter size here, with some 20 billion metal oxides field effect transistors. This is quite a spectacular advance. And so thanks to that, we now have smartphones. So this is what a free vacuum tube amplifier would look like, classical physics. And instead, in this little region over here, we have these multi-billion transistor chips over here. And thanks to this, we have our smartphones. So there's really a direct line in development from the first quantum theory of solids to straight to the telephone. People at Bell Labs realized that this was something that needed to be studied. So the first thing they learned quantum mechanics and then began to apply it throughout until 1947 and beyond. Well, that's really the end of the story I want to tell. And this was a very nice illustration of this. This is Bell saying to his assistant, Watson, now that I've invented it, I have this odd compulsion to hold my hand wherever I go and glance at it incessantly. And if you ride the subways here, you see these standard pictures of everybody looking at their phones. the sad, of course, he had a much larger telephone here. This way, yeah. But everybody's looking at telephones. It's quite an amazing phenomenon. And so when you look at, or when you see a batch of people looking at the telephones, think of the story of quantum mechanics that got people to that. It just didn't happen. They didn't go to Yodobashi and buy a camera and buy a telephone. A lot of work, a lot of thought went into this starting in the late 1880s. So, well, I think that's really the end of the story. I mean, but basically, the physicists, when they started studying the colors of metals, hot metals, and light emitted by atoms, realized just just about a century later, quantum physics would go on to change and really continue to change the world we live in. Now we can look forward to new developments in quantum mechanics, quantum computers, quantum information, quantum anything else. And so it's really, I think, a remarkable intellectual development here. So I say thank you. Domo arigato.